Okay, in this next part, there's a very important phrase that's going to show up on the test. I know because I made these tests. And it's eliminate the parameter. And basically what that means is, when you eliminate the parameter, that you can have only x and y in the equation. So you don't want anything besides x and y. Or in other words, no t in this particular example. Now, in some equations, this is super easy. Like, you're just going to laugh when you see this, but this is what happens. Take a look at the t value right here. See it? Do you see that there's also a t over there? That means that everywhere you see a t, you can replace it with whatever the t equals. So in other words, y equals 1/2 times x. Because this is what your t was. It's called substitution. Probably learned that for the very first time back in Algebra 1. And then you just graph it. So 1, 2, 3, 4, 1, 2, 3, 4. I see that my y-intercept is 0, so I plot 0. And then my slope is half, so I go up 1 over 2. And there's my line. Oh, there's a letter that comes before P.
Thank you.
In number 6, what we're going to do this time instead is we are going to go backwards. Instead of eliminating the parameter, we're going to create parametric equations. So the cool thing is, when you're creating parametric equations, you start with what they call function notation, y equals x squared plus 1. This is a parabola, right, that has its vertex at 0, 1 and opens up. And you're going to create an x and y equation that represents the same exact thing. No big deal. They're saying that you can choose whatever you want to be your parameter. You can choose whatever you want to be your parameter. Let me show you what I mean. In the first one, they tell us that they choose the t, the parameter, to be x. So I'm just going to cross this off for a second. So they're going to say, hey, my x, that's going to be my parameter. They wrote it back over here as t is x. Whatever, that's fine. If I do use that, I could take that t that they said was the x, and everywhere I see the x, shove it in there. Which means then my y would be equal to
T squared plus
t squared plus 1. This is a set of parametric equations. This two equation set, x equals t and y equals t squared plus 1, is the same as the orange highlight, but in parametric form. Why? Because I chose the x to be t. What if I chose something else to be t? So down below, they say, let's try something different. Let's say the t is, instead of being x, x minus 2. Well, that kind of messes me up, because I'm not used to seeing the t equals something. I'm used to seeing x equals something. What do? No big deal. Just rearrange it. Move the 2 to the other side. And that means x is equal to t plus 2. I just move the 2 over by adding 2 to both sides of the equation. Then my y will be equal to t plus 2 squared plus 1. Because this stuff right here was what the x value was. Now that still might be a little bit confusing, so let's totally try something different. Let's say the t is going to be equal to motion. No, we're not going to do
LOL.
Cocoa butter.
No. That's not really going to work because I need an x, right? So that's ridiculous. So let's start with x. Let's say that my x is equal to lotion, is what I meant to say. And now my parameter is called lotion instead of t. And my y equation would be lotion squared plus 1. This set of parametric equations is the same as the other two, even though it's using the word lotion. When you go to your calculator, instead of typing in the word lotion into your parametric equations, your calculator is going to use the letter
T.
T.
T squared.
Joe, stop. In the last problem that we're going to do together, when they ask us to eliminate the parameter, Joe, what does eliminate the parameter mean?
Eliminate. Eliminate.
So let's take a look at this graph in degrees, in parametric mode, and see what happens. So the first thing that we had was the cosine of theta, which is actually going to show up as a t. And the second thing is going to show up as 3 sine of t. What the?
Natural log.
Thought I hit sine, sorry. And then as I graph this, I'm going to actually go back up and change. Actually, I'll just leave the draw on. That's fine. I'm going to go to my window. Now remember, Anna told me that she was in degrees. So when I'm in degrees, I'm going to go from 0 degrees to 360 degrees. And I'm going to go up by 1 degree at a time. And for my x and y values, I think I'm going to go from -5. This might not work out, but I'm going to go from -5 to 5 in either direction. And then I'm going to graph it. Okay, take a look. Watch it. Which direction is it going? Say up, I'm going to smack you in the head. We learned about this in chapter 4.
Counterclockwise.
Thank you very much, Joe. Counterclockwise is correct. And you can see an ellipse. Where's the center of our ellipse? 0, 0. How far did I go up and down in the y direction from the center? 3. How about left and right? 1. So I want you to be paying attention to that as we go back to the paper and pencil, and I show you how it works out in the paper and pencil that we have an ellipse. Okay, so you can do this on your calculator. You can also do it by hand. Obviously going up by 1 is not very fast. And I use degrees, so that's why I had from 0 to 360. Now let's go look at our paper. Whenever you see eliminate the parameter, and you also notice that you have sines and cosines, you are going to use the following equation. Cosine squared theta plus sine squared theta equals 1. This is the most famous trig identity that we learned when we learned the unit circle. It's the same as the Pythagorean theorem. We talked about this. This was, in case you don't remember, when we talked about the unit circle. We had this unit circle and there was a triangle. Looked like this. The cosine was this side, the sine was this side, and the radius was 1. Cosine squared plus sine squared equals 1. Pythagorean theorem. As I look at what's going on, you need to recall that this equation really means this. And they use the notation where the 2's in between the words and the parameter, because otherwise if they put it after the theta, which is the angle, that means the angle is being squared. And they had to have another way to denote that. So I notice that I have two things here. And look at this. Cosine. Cosine. Notice it?
Mm-hmm.
That means that the stuff inside the blue parentheses is really the same as x from our equation up above. And then, in the second one, oh, don't forget it's squared. In the second one, I have whatever the sine is. Oh, shoot, I didn't rearrange that one. Maybe I should do that. So if I rearrange this equation, that really means that my sine of theta is equal to y over 3. Or in other words, because we're really clever, we can do this. Because the y on top is being squared, that's how we got the y minus 0 squared. The 3 on the bottom is being squared, that's how we got the 9. And this is what we just learned in the previous sections. And so if I went to go graph that, I know that my center is at 0, 0. And I also know that I'm going up and down 3 units from the center in the y direction, that is, because the 9 was under the y, and we learned that you take the square root of that number. I'm going left and right 1 unit, because there's a 1 under the x squared thing. And if we watched the video from when we graphed this on our calculator, we know that our graph was moving in a counterclockwise direction, correct? So the big idea is whenever you see sines and cosines, make sure you use the red equation up above to eliminate your parameter.